Welcome back to the Deep Dive. Today we are tackling a topic that is so fundamental to our daily existence that we almost never stop to think about how weird it actually is.
We really don't.
We are talking about vision.
It is the dominant sense for us. I mean, we are incredibly visual creatures, and because it feels so effortless, you open your eyes and the world is instantly there. We tend to assume the mechanism is simple.
Oh, absolutely. The intuition is that the eye is a camera, it's a lens, it snaps photo and sends that photo to the brain.
Like a perfect high-fidelity video feed.
Exactly. It feels immediate. It feels authoritative. If I see it, it must be true. It feels like a live stream of reality.
Sure.
But looking at our stack of sources today, and we have the absolute heavy hitters, Ganon's review of medical physiology and Guyton and Hall's textbook of medical physiology, the reality described in there is so much messier, so much noisier, and frankly, so much more fascinating than a simple camera.
It really is. I think the central tension of this whole deep dive is going to be exactly that disconnect. The sensation of vision is perfect, it's seamless, it's high definition. But the physiological reality is that the eye is capturing a noisy, inverted, two-dimensional image that's full of gaps and blind spots. And the brain is just frantically working to reconstruct, interpret, and edit that data.
To basically hallucinate what we call sight.
That's a great way to put it. It's a controlled hallucination based on sensory input.
I love that. So here is our mission today. We're going to synthesize these two massive textbooks. We'll use Ganon, as we often do, for the mechanistic nuts and bolts.
Yeah.
You know, the cellular stuff, the chemistry, the ions.
Yeah, Ganon is fantastic for that level of detail.
And we use Guyton for the systems level blueprint, the optics, the regulation, the big picture of how it all fits together.
And just a quick disclaimer before we really get going, this is a conceptual map. We are going to build a scaffold for your understanding, but this does not replace sitting down and actually reading the chapters on the eye, the retina, and central neurophysiology.
Absolutely not. You need to see the diagrams. You need to trace the pathways yourself.
Yeah.
Consider us your tour guides through the dense jungle of text.
Exactly. Use this to orient yourself before you go in or to consolidate after.
So the one theme we really want you to keep in your mind today is active interpretation.
The eye is not a passive receiver. It is an active editor.
And the other big one is trade-offs.
Oh, constantly. You'll see this over and over. Sensitivity versus acuity, speed versus detail. The entire system is built on a series of really clever compromises.
All right, let's jump in. Section 1, the optics, the hardware. Before the brain can process anything, we have to get light from the outside world onto the back of the eyeball.
Right, and this brings us straight into the physics of refraction.
Which is really just a fancy word for bending light.
It is. Technically, Guyton defines refraction as the bending of light rays at an angulated interface between media of different densities.
Okay, let's pause on that definition because every word there matters. Angulated interface between media of different densities. Why is the density the key factor here?
Because light travels at different speeds through different materials. It's fastest in a vacuum, almost as fast in air. But when it hits a denser material, say water or glass or the cornea, it slows down.
Okay, that makes sense.
Now, if it hits that interface straight on at a 90-degree angle, perpendicular, it just slows down but keeps going straight. But, and this is the key, if it hits at an angle, the part of the light wave that hits the dense medium first slows down before the rest of the wave.
Oh, I see. It's like a car driving from pavement onto a patch of sand, but only the right side wheels hit the sand first.
That is a perfect analogy. The right side slows down, the left side is still moving fast on the pavement, and the whole car just pivots. It turns.
And that turn is refraction.
That is refraction. And we measure the slowing power of a material with something called the refractive index. Air is the baseline. It's set at 1.00. Everything else is compared to that.
So knowing that, here's a question for you and for everyone listening. When you think of the eye focusing light, what's the first anatomical part that comes to mind?
Almost everyone says the lens. I mean, it's in the name. It's the lens of the eye.
Right, it's the star of the show. But if you actually look at the numbers in Guyton, that's not the main player at all.
Not even close. And this is where that refractive index is so important. The cornea, that clear front window of the eye, has a refractive index of about 1.38.
Okay.
Now, the lens has an index of about 1.40, so they're almost the same density. But remember, refraction happens at the difference between two media.
So the light is coming from the air, which is 1.00, and it's slamming into the cornea at 1.38.
That is a massive jump in density. That is where the light hits the brakes, so to speak, and bends the most. The cornea provides about 2/3 of the total refractive power of the eye.
A full 2/3. That's incredible. So the lens is really just for fine-tuning.
Well, think about where the lens is physically located. It's not in the air, it's inside the eye. And it's bathed in aqueous humor on one side and vitreous humor on the other.
Right.
Those fluids have refractive indices of around 1.33 or 1.34. The lens is 1.40. The difference is tiny. So that interface only provides about 1/3 of the total bending power.
It's a much more gentle turn.
Much more gentle turn. So the cornea does the big coarse focusing and the lens does the fine-tuning.
So Guyton talks about this concept of the reduced eye. Is that just a way to simplify all this math so medical students don't, cry?
Essentially, yes. It's a conceptual model. If you try to calculate the refraction at the front of the cornea, then the back of the cornea, then the front of the lens, then the back of the lens, the math gets horrific.
I can imagine.
So Guyton simplifies it. He says, let's just pretend the entire optical system of the eye is a single lens. We'll put its central point about 17 millimeters in front of the retina, and we'll give it a total power.
And what's the total power of this reduced eye?
About 59 diopters.
59 diopters. Just for context, a pair of over-the-counter reading glasses is usually what, plus 1.5 or plus 2.0?
Exactly. So the eye's optical system is incredibly powerful.
But if the cornea is fixed, if it's doing most of the heavy lifting and you can't change its shape, why do we even need a lens? Why not just have a really, really powerful cornea and be done with it?
Because the cornea is rigid. It's set. If you only had a cornea, you would be permanently focused at one single distance. Anything closer or further away would be blurry.
You'd be a fixed focus camera.
Fixed focus camera. The lens provides the variable focus. It provides accommodation.
Okay, let's unpack accommodation. This mechanism is one of those classic physiological paradoxes that always trips people up because it feels like it works backward from how you'd expect a muscle to work.
It really does. To get it, you have to visualize the anatomy. The lens itself is elastic. It's like a little rubber ball that naturally wants to be round and fat. But it's suspended inside the eye by a ring of about 70 ligaments called the suspensory ligaments.
Like a trampoline, with the lens as the mat and the ligaments as the springs.
That's a perfect way to think of it, yeah. The ligaments are pulling it tight from all sides. Now, in the resting state, when you are looking at something far away, like the horizon, these ligaments are under high tension. They are constantly pulling the lens and stretching it flat.
So when your eye is relaxed, looking at a distance, the ligaments are tight and the lens is flat.
Correct. A flat lens is a weak lens. It doesn't bend light very much, which is what you need for parallel rays coming from a distant object.
Okay, that makes sense. Now suppose I want to look at my phone. It's close to my face. I need to focus up close.
Now you need a strong lens. You need a round, fat, convex lens to bend the light more sharply. To get that, you need to relax those ligaments. You need to release the tension.
And to relax the ligaments, and this is the weird part, I have to contract a muscle.
That is the twist. The ciliary muscle is a sphincter. It's a ring of smooth muscle that surrounds the lens. And when a ring-shaped muscle contracts, what happens to the hole in the middle?
The hole gets smaller.
It gets smaller. So the muscle tightens, the ring shrinks, and the attachment points for those ligaments move inward, closer to the lens.
Which introduces slack into the ligaments, like
Yeah.
loosening the springs on the trampoline.
Exactly. And once that tension is gone, the lens, because of its own natural elasticity, just bulges out. It becomes round and fat.
So let's trace that one more time. Muscle contraction leads to ligament relaxation, which allows the lens to bulge, and that gives you near vision.
You've got it. It's entirely dependent on the natural elasticity of the lens to rebound into its preferred spherical shape once the tension is off.
And this is all controlled by the parasympathetic nervous system.
It is, which makes a certain amount of sense. Parasympathetic is rest and digest. That's when you'd be reading a book or looking at your food up close.
And the sympathetic system, fight or flight.
That tends to relax the ciliary muscle, which tightens the ligaments and flattens the lens for distance vision. You want to see the lion on the horizon, not the details of the grass at your feet.
But this entire elegant system has a built-in flaw, doesn't it? It relies on the lens being elastic.
It does, and that brings us to presbyopia.
The old eye.
It's fundamentally a protein issue. As we age, the proteins inside the lens start to denature. They cross-link, they get hard, they get sclerotic. The capsule itself loses its elasticity.
So you could be 50 years old and your ciliary muscle is contracting perfectly, your parasympathetic nerves are firing just fine, creating all the slack in the world.
But the lens just sits there. It's become too stiff to bulge. It refuses to change shape.
It's like trying to inflate a bowling ball.
Exactly. Guyton has this incredible chart showing the power of accommodation over a lifetime. It drops from about 14 diopters in a child to maybe 2 diopters by age 50, and it's essentially 0 by age 70.
0. So you actually become a fixed focus camera at that point.
You do. Your eyes become permanently set to a specific focal distance. That's why reading glasses become absolutely mandatory. You need an external glass lens to do the extra bending that your biological lens can no longer provide.
While we're on the topic of things going wrong with the optics, let's quickly run through the common bugs in the system, the refractive errors. Because almost nobody has truly perfect vision.
That's true. The clinical term for perfect vision is emetropia. It means parallel light rays from a distant object focus perfectly on the retina without any effort.
But then we have hyperopia. Most people know it as farsightedness.
Right. In hyperopia, the core problem is usually that the eyeball is too short or maybe the lens system's too weak. The light rays enter the eye and start converging, but they hit the back of the retina before they finish focusing.
So if you could see through the person's head, the actual focal point would be somewhere behind the eyeball.
Exactly. Which means the image that actually lands on the retina is just a blurry circle. To fix this, you need to help the eye converge the light faster. You need to give it a boost. So you use a convex lens, a plus lens.
And myopia, or nearsightedness, is the opposite problem.
The opposite. The eyeball is too long or the lens system is too strong. The light focuses in front of the retina. By the time the rays reach the actual photoreceptors, they've already crossed over and are starting to diverge again.
So distant objects are blurry. And the fix for that is a concave lens, a minus lens.
Right. The concave lens slightly diverges the rays before they even enter the eye, which effectively pushes the focal point backward onto the retina where it belongs.
And then there's astigmatism, which always sounds more serious than it usually is.
It's just a geometry problem. Instead of the cornea being perfectly spherical like a section of a basketball, it's shaped more like the side of an egg or a football. It has different curvatures and different planes.
So vertical lines might focus at one distance, and horizontal lines at another.
Precisely. You never get a single sharp focal point for the whole image. The fix is a cylindrical lens that corrects for that one specific axis of abnormal curvature.
Okay, one last thing on the hardware before we move inside the eye, the fluids. The eye isn't a solid object, it's pressurized.
It is, and this is critical. It's maintained by the aqueous humor. This is a fluid that's constantly being secreted by the ciliary processes, little finger-like projections behind the iris.
It's basically a plumbing system, isn't it?
It absolutely is. It's produced, it flows forward through the pupil into the anterior chamber, and then it drains out through a little sieve called the trabecular meshwork.
And this constant production and drainage creates pressure.
It does. It maintains an intraocular pressure of about 12 to 20 millimeters of mercury. This pressure is what keeps the eyeball inflated and spherical. If you lose pressure, the eyeball can collapse and the optics get completely distorted.
And if you have too much pressure,
that's glaucoma. The drain gets clogged, pressure builds up, and that pressure pushes back against the delicate structures in the back of the eye. It compresses the optic nerve and physically kills the nerve fibers.
A silent thief of sight.
It really is. Okay, so let's move back. The light has passed through the cornea, the aqueous humor, the lens, and the vitreous humor. It has been perfectly focused, and now it has hit the back of the eye. Welcome to the retina.
Section 2. The retina. The transducer.
This is where the magic happens. This is where light, which is electromagnetic radiation, becomes electricity. It becomes a neural signal.
And the first thing that just jumps out from the diagrams in both Ganong and Guyton is the layout, it seems. Well, it seems completely wrong. It looks like it was designed backward.
It really does. It's known as an inverted retina. To reach the photoreceptors, the rods and cones that actually detect the light, a photon, has to pass through the entire neural wiring of the retina first.
Wait, say that again. It goes through the output wires first.
Yes. It has to go through the ganglion cell layer, the amacrine cell layer, the bipolar cell layer, and the horizontal cell layer, just to get to the detectors, which are at the very, very back of the eye.
That's like putting the film behind all the camera mechanics. It just seems like a terrible design. It must degrade the image.
It does scatter the light slightly, yes, but there's a huge physiological reason for it, a massive constraint. The photoreceptors are unbelievably metabolically active. They are some of the most energy-hungry cells in the entire body.
They need a constant supply of fuel.
A massive constant supply. They need oxygen, they need nutrients, and they need to constantly cycle out old chemical components and bring in new ones. By sitting at the very back, they are right next to two critical support structures: the choroid, which is a rich layer of blood vessels, and the retinal pigment epithelium.
The pigment epithelium.
Yep.
That's that black layer you see in the back of the eye, right?
It is, and it serves two absolute crucial roles. One, it acts as the nursemaid to the photoreceptors. It feeds them, it takes away their waste, and it recycles key molecules for them. And two, it contains a large amount of melanin, the black pigment, which absorbs any stray light that the photoreceptors don't catch. Without it, light would bounce around inside the eyeball. This is called intraocular scattering, and it would just wash out the image completely.
So it's like painting the inside of a camera black to prevent reflections.
Precisely. So the backward wiring is a trade-off. We sacrifice a tiny little bit of optical clarity in order to keep the sensors alive and to keep the image sharp.
Except in one very specific spot, the fovea.
Yes. The fovea is our high-definition center. It's a tiny pit, about 1.5 millimeters in diameter, right in the center of the retina. And here, evolution came up with a clever solution.
It fixed the design flaw.
It did. In the fovea, the neural layers, the ganglion and bipolar cells, are physically pushed to the side. They are swept away.
It's like parting the Red Sea for the photons.
Exactly. It creates a clear, unobstructed path for light to hit the photoreceptors directly. And importantly, the fovea is exclusively populated by one type of photoreceptor, the cones.
This brings us to the stars of this show, the actual light detectors, the rods versus the cones.
This is a classic physiological trade-off. You can't have it all. The system had to choose between sensitivity and acuity.
Let's start with the rods. They're the workhorses of the retina.
They are. There are about 100 million rods in each eye, compared to only about 5 million cones. Rods are your night vision specialists. This is called scotopic vision. They are incredibly, exquisitely sensitive to light.
How sensitive?
They can reliably detect a single photon.
One single photon. One packet of light energy can trigger a response.
It can. The amplification in the system is just immense. But the trade-off is that they are colorblind and they have very low acuity or sharpness.
Why low acuity? If they're so sensitive, why isn't the image they produce sharp?
It comes down to the wiring. It's all about convergence. In the peripheral retina, you might have 100 or even more rods, all wiring into a single bipolar cell, and then many bipolar cells wiring into a single ganglion cell.
So the brain gets a signal from that ganglion cell that says, light is here in this general area, but it doesn't know exactly which one of those 100 rods sent the original signal.
Exactly. It's like having 100 tiny buttons all wired to one big light bulb. You know a button was pressed, but not which one. It's a very pixelated, low-resolution signal.
But the advantage is that a tiny signal from each of those 100 rods can all add up to be enough to trigger that one ganglion cell.
That's the key. High sensitivity, low resolution.
And the cones are the complete opposite.
The complete opposite. Cones are for photopic vision, or day vision. They are much less sensitive to light. They operate in bright conditions. They give us our color vision because we have 3 different types, blue, green, and red, each tuned to a different wavelength of light.
And their wiring.
In the fovea, the wiring is often one-to-one. One cone connects to one bipolar cell, connects to one ganglion cell.
So it's a dedicated private line to the brain. The brain knows exactly where that signal came from, down to a single receptor.
Precisely. Which gives you incredibly high resolution, incredible sharpness, and detail.
But the trade-off is low sensitivity. You need a lot more photons, a much brighter light, to trigger that single cone and send a signal all the way down that private line.
Exactly. And that's why you can't see colors in the dark. There's just not enough light to stimulate the cones. At night, you are relying entirely on your rods.
Okay, let's get into the molecular machine itself. How does a rod or a cone actually detect that photon? Gannon goes into some beautiful detail on the photochemistry here.
It all centers on a molecule called rhodopsin in the rods, or similar photopigments in the cones. Rhodopsin is a combination of a protein called scotoxin and a small pigment molecule called retinol.
And retinol is directly related to vitamin A, right?
That is. Retinol is the aldehyde of vitamin A. That's a direct clinical link. If you have a severe vitamin A deficiency, you can't produce enough retinol.
You literally run out of the raw material to make the light sensor.
You do. And the first symptom is night blindness, because the rods are affected first. The pigment epithelium in the back of the eye actually serves as a major storage site for vitamin A for this very reason.
So in the dark, when the rod is just waiting for a photon, what does this rhodopsin molecule look like?
In the dark, the retinal component is in a specific bent shape. It's called 11-cis retinal. You can think of it as a bent spring, and it's locked snugly into a pocket on the scotopsin protein. This is its stable resting state.
And then a photon of light comes in and hits it.
The energy of that single photon is just enough to physically kick the molecule. It provides the activation energy to cause it to straighten out. It instantly converts from the bent 11-cis form to a straight all-trans form.
This shape change is the key event.
It is the only thing that light does in the entire process of vision. Everything that follows is a dark chemical cascade. And because the retinal has changed shape, it no longer fits snugly in the protein pocket. It starts to pull away.
And this is the process people refer to as bleaching.
Yes. As the retinal pulls away, it creates a series of incredibly short-lived, unstable intermediates. You get bathorodopsin, then lumerodopsin, then metarodopsin the second. But the one you really need to remember is metarodopsin second.
Why is that one so important?
Metarodopsin second is the active form. It's the trigger. It is the molecule that actually kicks off the electrical signal in the cell. After it does its job, the all-trans retinal separates completely from the opsin, and you have to use metabolic energy with an enzyme called retinal isomerase to twist it back into the 11-cis shape and reattach it.
Which takes time and energy.
It does. But here's where it gets really, really interesting. We need to talk about what that metarodopsin II actually does to the cell's electrical state. This is section 3. Phototransduction. And this is my favorite part of visual physiology because it is completely backward from what you would ever expect.
Right. Most sensory receptors we think of, like touch receptors or pain receptors, when you stimulate them, they depolarize. They get excited, their voltage goes up, and they fire.
Exactly. You poke a touch receptor, sodium channels open, sodium rushes in, the cell becomes more positive, and it fires an action potential. Simple. But photoreceptors, when you hit them with their stimulus, light, they hyperpolarize.
They become more negative. They effectively turn off.
They turn off. The signal for light is the receptor becoming silent. To understand this, you have to understand something called the dark current.
Let's unpack the dark current, because this implies that in total pitch black darkness, my photoreceptors are working incredibly hard.
They are burning a huge amount of energy. In the dark, the rod has very high levels of an intracellular messenger molecule called cyclic GMP, or cGMP.
Hi.
This cGMP acts like a key, or maybe a doorstop. It binds directly to sodium channels in the outer segment of the rod and physically holds them open.
So in the dark, sodium is just constantly leaking into the cell.
Yes, a steady inward leak of positive charge. This makes the cell relatively positive or depolarized compared to a typical neuron. It rests at about negative 40 millivolts.
And because it's depolarized at rest, it is constantly releasing neurotransmitter from its synaptic terminal, specifically glutamate.
That's the punchline. In the pitch black, your photoreceptors are continuously dumping glutamate onto the next cells in the chain. The signal for darkness is a constant barrage of glutamate.
Okay, so now the light hits. The photon arrives. We've created metarodopsin II. What happens next?
We trigger an amplification cascade. This is how we get from one photon to a measurable electrical signal. It is a masterpiece of biological engineering.
Walk us through it.
Step 1. That one molecule of metarodopsin II activates a G protein called transducin. It's a G protein coupled receptor. But instead of activating hundreds of G proteins over time, it does so very rapidly.
Okay, so one active rhodopsin bumps into many transducin molecules. Amplification, step 1.
Exactly. Now, step 2. Each of those activated transducin molecules then activates an enzyme. The enzyme is called cGMP phosphodiesterase.
Phosphodiesterase, that's an enzyme that breaks down molecules, right?
Yeah. It breaks down cGMP. It's like a little Pac-Man that just chews up all the cGMP in the cell. So as soon as this enzyme is activated, the levels of cGMP inside the cell plummet.
And since cGMP was the doorstop holding the sodium channels open,
The doorstop is gone, the sodium channels slam shut, but the potassium pumps in the inner segment are still working, constantly pumping positive potassium ions out of the cell.
so the positive charge stops coming in, but it keeps going out.
Right. The inside of the cell becomes rapidly more negative. It hyperpolarizes, dropping from negative 40 millivolts down to negative 70 or negative 80.
And because the cell is now hyperpolarized, it stops releasing glutamate.
Precisely. So the signal for light is actually the sudden, dramatic silence of the glutamate release.
The message is the absence of a message.
It is. And the beauty of this cascade is the incredible game. One photon activates one rhodopsin. That one rhodopsin activates hundreds of transducins. Each transducin activates one phosphodiesterase, but that enzyme can then destroy thousands of cGMP molecules. The end result is that one single photon can cause the closure of millions of sodium channels.
That's massive amplification.
Massive. It allows the rod to register the faintest whisper of light in a dark room.
It's just incredible engineering. But the signal, this drop in glutamate, isn't just sent raw to the brain. This brings us to section 4, retinal processing. The retina does a whole lot of Photoshop work on the image before the brain even knows what's happening.
It absolutely does. The retina is really a piece of the brain that has grown out into the eye during development. It's a full-on neural processing center. It processes contrast, edges, motion. It compresses the data significantly.
Let's talk about adaptation first. That experience of walking out of a dark movie theater into bright sunlight, it physically hurts. You're completely blinded for a moment, then a minute later, you're totally fine.
That's light and dark adaptation. The challenge here is immense. The visual system has to operate over a range of light intensity that spans 10 log units. That is a factor of 10 billion, from a starlit night to a sunny beach.
No camera on Earth can do that. How does the system handle that incredible range?
It uses multiple mechanisms on different timescales. The fastest is pupillary constriction. The iris closes down. That can give you maybe a 30-fold reduction in light entering the eye.
Okay, that's a start, but 30-fold isn't 10 billion-fold.
Not even close. So the real work is biochemical and neural. In bright light, you bleach your photopigments. You break down so much of the rhodopsin that there's simply less of it available to catch photons. You are effectively turning down the gain on the receptors themselves.
And dark adaptation is just the reverse of that process.
It is. You walk into a dark room, and at first, you can't see anything. All your photopigment is bleached. You have to wait for the enzymes in the retina to slowly, metabolically rebuild the rhodopsin stores.
It just takes a while.
It does. Cones adapt quite fast, within a few minutes, but they only get so sensitive. Rods are much slower. It can take 20 to 40 minutes to fully dark adapt, but their sensitivity can increase up to 25,000-fold.
That explains that feeling where you just keep seeing better and better the longer you sit in the dark.
Exactly, you're regenerating your rhodopsin. Now let's look at the circuitry. The interneurons that sit between the photoreceptors and the output cells. The horizontal cells, the bipolar cells, and the amacrine cells.
The horizontal cells are famous for being responsible for a phenomenon called lateral inhibition. This seems to be a key concept for creating sharpness.
It is absolutely fundamental to how we perceive edges. It's a brilliant bit of neural computation. Imagine a beam of light hitting a spot on the retina. The photoreceptors in the center of that spot are strongly activated.
Okay.
They send a strong signal downward to the bipolar cells, but they also send a signal sideways to the horizontal cells. And the horizontal cells do exactly what their name implies. They reach out horizontally and connect to the neighboring pathways, and they inhibit them.
So the photoreceptor in the center is yelling, "I see light," and it's simultaneously telling its immediate neighbors, "Be quiet."
Exactly. I am the important one right now. This creates a mechanism where the signal is strong in the center, but the surrounding area is actively suppressed below its baseline. This sharpens the contrast right at the edge of the light.
It stops the signal from just spreading out and blurring.
It keeps the image crisp. It accentuates borders. Our visual system doesn't care so much about absolute brightness. It cares immensely about differences in brightness. It's an edge detector.
And this leads to the strange organization of the ganglion cells, the output cells. They have these on-center and off-center receptive fields.
This is a direct consequence of that lateral inhibition. It's fascinating. You have some ganglion cells that fire rapidly only when light hits the tiny center of their receptive field. We call those on-center cells.
Okay.
But you have a whole other population of cells that do the opposite. They fire rapidly when the center of their field is dark and the donut-shaped surround is illuminated. Those are off-center cells.
So the brain has a dedicated detector for a bright spot on a dark background and a dedicated detector for a dark spot on a bright background.
Yes. We don't just detect light. We detect contrast. We detect shadows and silhouettes just as actively as we detect illumination. It's two parallel channels of information going to the brain.
And these ganglion cells, the output neurons that form the optic nerve, they aren't all the same, are they? Guyton and Ganong both talk about M cells and Key cells.
Right. These are the two great data streams leaving the eye. M cells are magnocellular cells. Magno means large. These are big cells with big receptive fields. They get a lot of input from the rods.
And what information are they carrying? What do they care about?
They care about where and when. They are all about motion, speed, flicker, and the general location of an object. They are colorblind and have low spatial resolution, but they have very high temporal resolution. They're fast. They're the motion detectors.
They tell you something is moving over there.
Exactly. And then you have the P cells, or parvocellular cells. Parvo means small. These are small cells with small, detailed receptive fields. They get their input from the cones.
And they must care about the details.
They care about what? They carry high-resolution information about fine detail, texture, and critically color. They are much slower than the M cells, but they provide the richness of the visual scene.
So the M stream is shouting, "A truck is coming fast." And the P stream is calmly reporting, "It's a red Ford F-150 with a small dent in the front bumper."
That is a perfect analogy, and what's amazing is that these two streams stay almost completely separated all the way up through the brain.
Which brings us to section 5. The central pathways, the information superhighway to the brain.
Right. So the axons of those M and P ganglion cells bundle together to form the optic nerve. Each eye has one. And then we hit a critical junction point at the base of the brain, the optic chiasm.
The great crossroads.
This is so critical for clinicians to understand. At the chiasm, the fibers from the nasal half of each retina, the side closer to your nose, cross over to the other side of the brain. But the fibers from the temporal half, the side closer to your ear, stay on the same side.
Why do they do that? What's the purpose of this partial crossing?
It's to bring the visual fields together. Think about your left visual field. Everything to the left of your nose. That light falls on the nasal half of your left retina and the temporal half of your right retina.
Okay, I think I'm following.
By crossing just the nasal fibers over, the brain ensures that all the information from the left visual field from both eyes ends up in the right hemisphere of the brain. And all the information from the right visual field ends up in the left hemisphere.
It reassembles the world map in the correct hemispheres.
Exactly. And this allows doctors to pinpoint the location of brain damage based on vision loss. If you cut the left optic nerve before the chiasm, you go blind in the left eye. Simple.
Right.
But if you have a tumor, say a pituitary tumor, that presses on the center of the chiasm where the nasal fibers are crossing,
You'd lose the information from the nasal retinas of both eyes, which corresponds to the temporal or outer visual fields.
exactly, you get bitemporal hemianopia, tunnel vision, and if you have a stroke that damages the optic tract after the chiasm, you lose the entire opposite visual field in both eyes. That's called a homonymous hemianopia.
So after the chiasm, the signals travel in the optic tract to the thalamus, specifically to a little nucleus called the lateral geniculate nucleus, or LGN.
The great gatekeeper of vision, the LGN is not just a passive cable splice. It's a highly organized six-layered structure.
And those M and P streams we talked about.
They stay segregated. The big M cell synapse in layers 1 and 2, the smaller P cell synapse in layers 3 through 6. It keeps the where and what information separate. But crucially, the LGN receives a massive amount of feedback from the visual cortex and from the reticular formation in the brainstem.
So the brain can actively tell the LGN, "I'm not interested in that right now. Turn down the volume."
Precisely. It's an attention filter. It gates the flow of information before it ever reaches consciousness. If you are sleeping or focusing intently on a sound, the LGN can inhibit the visual signal so it doesn't distract you.
And then finally, from the LGN, the signals are sent via the optic radiations to their final destination, the primary visual cortex, V1, also called the striate cortex.
Right, located in the occipital lobe at the very back of your head. And when the visual map arrives here, it's incredibly distorted. The fovea, that tiny high-res center of the retina, takes up a massive, disproportionate amount of cortical real estate.
What do you mean by disproportionate?
I mean, the fovea accounts for less than 0.01% of the retinal area, but it gets about 50% of the processing power in V1. It's a phenomenon called cortical magnification.
It's like a map of the United States where New York City is physically the size of Texas.
That's a great way to put it. It reflects the immense computational power required to process all that high acuity, detailed information from the P cells.
Now, inside V1, this is where we find those famous feature detectors that were discovered by Hubel and Meisel, the simple and complex cells.
Yes, their Nobel Prize-winning work. They put microelectrodes into the visual cortex of cats and monkeys and showed them images, trying to figure out what made the neurons fire. And they found that neurons in V1 don't respond to complex things like faces or chairs.
They respond to something much more basic.
They respond to lines and edges at very specific angles. A simple cell might fire wildly, but only if it sees a vertical bar of light in one specific spot in the visual field. If you tilt that bar just 10 degrees, the cell goes completely silent.
It's an orientation detector.
A very precise one. And then you have complex cells, which are the next level up. They also have a preferred orientation, say a horizontal line, but they don't care exactly where it is in their receptive field, as long as it's moving in a specific direction.
So they're tracking the movement of oriented edges.
Exactly. So V1 is basically deconstructing the entire visual world into a sketch. It's a map of outlines and edges and their angles of orientation. It breaks reality down into its most basic geometric components.
And it keeps things organized in these incredible columns. Ocular dominance columns, which are like zebra stripes of alternating left eye and right eye input, and orientation columns for all the different angles.
It's a beautiful crystalline structure, but it's still just a sketch. The question is, where does it all come back together? That's section 6, advanced processing and movement.
The director's cut.
Right. The signal leaves V1 and splits again, heading out into the secondary visual areas, and it splits back into those two streams we hinted at with the M and P cells. The dorsal stream, the WARE pathway, goes up from the occipital lobe into the parietal lobe.
And it's taking that M cell data, the motion data.
Yes. This pathway analyzes 3D space, position, motion, and the gross form of objects. It guides your physical interactions with the world. It's what allows you to reach out and accurately grab your coffee cup.
And the ventral stream.
The what pathway? It goes down from the occipital lobe into the temporal lobe. It takes the P cell data, the color, and the fine detail. This pathway is responsible for object recognition. It's where you recognize that the object you're reaching for is, in fact, your coffee cup and not a stapler.
So damage to the dorsal stream would mean you could see the cup and describe it perfectly, but you couldn't accurately reach for it.
That's a condition called optic ataxia. And conversely, damage to the ventral stream might leave you able to grab the cup perfectly, but you wouldn't be able to recognize it as a cup. You'd have no idea what it was. That's visual agnosia.
I want to touch on color perception again here because that active interpretation theme is so strong. We have 3 types of cones, red, green, and blue. But we see millions of different colors. How?
It's all about ratios. It's a theory called trichromacy. The brain isn't just listening to one cone type at a time. It's constantly comparing the firing rate of all 3.
So if it's getting a signal that the red cones are firing at 100%, the green at 50%, and the blue at 0%, it computes that ratio.
And you perceive the color orange. If red is 0, green is 0, and blue is 100%, you see blue. If all 3 are firing equally and strongly, you perceive white. It's a combinatorial code.
And then the opponent process theory adds another layer on top of that.
It does. At the level of the ganglion cells and the cortex, the brain wires these cone inputs in opposition to each other. You have a red versus green channel and a blue versus yellow channel. That's why you can imagine a reddish yellow, orange, or a bluish green, cyan, but you can never imagine a reddish green.
They are mutually exclusive channels in the brain. If one is on, the other's off.
Exactly. But the most amazing brain trick of all is color constancy.
Okay, what's that?
If you look at a red apple outside in the bright white sunlight, it's reflecting a certain spectrum of wavelengths into your eye. Now, take that same apple inside and look at it under a yellowish incandescent light bulb. The physical wavelengths reflecting off it are now totally different.
Right. A camera would see a yellowish-orange apple.
It would, but your brain doesn't. Your brain subtracts the color of the ambient lighting. It calculates the difference, and it knows the apple is still red. It corrects the color to match your expectation of what reality should be.
That is wild. It's actively rewriting the raw data to make sense of the world.
It's a constant process of inference and correction.
We also have to talk briefly about eye movements, because we think we move our eyes smoothly across a page or a room, but we mostly don't.
We mostly don't. We do have a capacity for smooth pursuit, which is when you lock your gaze onto a moving object like following a bird flying across the sky. That requires complex cortical computation. But most of the time we use saccades.
The jerky jumps.
Rapid, ballistic, jerky movements. You pick a target in your peripheral vision, and your eyes jump to it in a fraction of a second. But here is the absolutely insane part. During that jump, the brain turns off the camera.
It's called saccadic suppression.
You are functionally blind for the split second while your eyes are in motion. The brain just stops processing the input, but you never, ever notice it. The brain just stitches the 2 static images, the one from before the saccade and the one from after, together seamlessly. It edits out the motion blur.
So our visual experience of a continuous, stable world is a complete illusion. It's actually a series of still frames with the messy transitions edited out.
Constant cuts. And there are even tinier movements, too. Even when you are trying to stare at a fixed point, your eyes are making these microscopic tremors, drifts, and flicks
Why would they do that?
to prevent adaptation. It's a brilliant solution. If you could hold an image perfectly still on the retina, the photoreceptors would bleach out and stop responding within seconds. The image would literally fade to gray and disappear. The eye has to keep jittering the image across the receptors to keep the signals fresh.
Unbelievable. The system has to introduce noise to maintain the signal. Finally, let's touch on stereopsis, depth perception.
This is pure geometry. Your eyes are a few inches apart, so they see the world from two slightly different angles. The brain's job is to calculate the retinal disparity, the tiny difference between the image falling on your left eye and the image on your right.
And it uses that difference to calculate distance.
It does. If the disparity is big, the object must be very close. If the disparity is small, the object must be far away. It's incredibly effective for nearby objects up to about 200 feet. After that, the disparity is too small to be useful, and we have to rely on other cues like size, shadow, and parallax.
So let's try to bring this all home. The central theme was active interpretation. Let's synthesize that.
Okay, think about the entire journey we just described. It starts with a single photon of light, physically flipping the shape of a protein molecule.
The only role of light.
Right. That chemical change then triggers a complex electrical cascade that results in a cell turning off. The absence of a signal becomes the signal. The retina then immediately compares that cell to its neighbors to find an edge, sharpening the image before it's even left the eye. The signal travels to the brain, gets split into separate streams for motion and detail,
The M&P pathways.
and then V1 breaks it all down into a primal sketch of lines and angles. Then the secondary areas paint in the color, identify the shape, and map its location in 3D space.
And all the while, the brain is stitching the jerky saccades together, stabilizing the image, filling in your blind spot, correcting the color based on the ambient lighting.
And it presents you with a seamless, stable, high-definition, real-time experience called sight.
It is not a camera, it's a full-blown construction site.
It creates a useful representation for survival. That's the key takeaway from Gaiden. The visual system doesn't care about being pixel perfect. It cares about edges, motion, contrast, and recognition. It gives you the information you need to not walk into walls and to find food.
That is a profound thought. We don't see reality, we see the version of reality we need to see to survive it.
Exactly. The map is not the territory.
So here's my final provocative thought for you, the listener. The next time you're just sitting somewhere, put down your device, look at a simple object in the room, a coffee mug, a book, and try to deconstruct it. Don't just see mug. Try to see the edges where the light changes and realize that your horizontal cells are creating that sharpness. Try to feel the depth calculation your eyes are making. Try to realize that the red of the mug is a calculation your brain is making based on wavelength ratios, not an inherent property of the mug itself.
It's a trippy exercise.
It is. Separating the sensation from the perception brings you so much closer to understanding this incredible physiology.
And remember, read the chapters, the details on the G proteins, the different types of amacrine cells, the layers of the LGN. They are in there, and they are beautiful.
Thanks for diving in with us. We'll see you on the next one.
See you then.